friends. All right, let's go. All right, y'all, so welcome today. So my name is Nyah Macklin. I'm going to be giving you all the energy, the excitement, the technical depth that we're going to get in today. But first of all, welcome so much. Welcome to Unlocking AI's Hidden Connections with Graphs. So I'm sure not a lot of people, especially this being a JavaScript developer conference, I'm a JavaScript engineer myself, TypeScript as well, but has anyone ever worked with graphs before? Okay, and I'm not talking about the bar charts, y'all, like for real, like neural networks, yeah. Awesome, well, all right, so I also want to ask, like, how many of us have actually shipped an agent, not just as a demo, but actually to production? Okay, I see a couple of hands. All right, so how many of us have had that agent do something wrong in production? Yes, most of the hands that already went up. So today, I'm actually going to show you all how to fix that, right? And I'm not going to talk to you about a new framework or a new wrapper around an LLM, but specifically, I'm going to talk to you about a specific data architecture that's going to give your agents some of the rigor that you've already had within your database architectures, and we'll cover how to model that work, how to index it, and how to enforce consistency and reliability today. So let's dive right in. So again, my name is Nyah Macklin. I'm a senior software engineer at Neo4j, and I work on graph algorithms, context engineering, and how to apply these to agentic systems. So I spent a lot of time, just like the intro just said, talking about AI governance and safety. And that actually turns out to matter a lot when thinking about our agent and the decisions that those agents are making. So before we get started, I like to always do selfie! All right, everyone smile. 1, 2, 3. Woo, 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 woo. Love it. Awesome. Okay, so we got that out the way. So let's get into this. All right, so I have an example here. I'm a JavaScript engineer myself. So who here, and you'll see some bugs in this code, right? Who here has tried to stitch 2 API responses from a fetch together by ID before? Who's tried to do that before? Okay, a lot of folk, right? And who's watched that break? Yeah! It happens every day. Like, it happened to me, especially when I was a founding engineer at another startup. Like, literally took down prod struggling, just struggle busting it, right? So you're doing this fetch, right? So you're fetching from users from one specific endpoint, and then you're fetching maybe orders or what have you from another endpoint, and then you're trying to write a loop in order to loop them together by ID, right? And most of us have done that. But now, you know, that goes on and breaks, and then the IDs aren't actually lining up, right? Half of the screen is suddenly undefined. I'm banging my head across. I'm like, why won't you work? But we notice specifically how that code broke, right? We knew the second that it happened. Most people caught that bug immediately. The link was right there in the data, and in order to the data specifically was trying to carry along that user ID. But it wasn't real within our system. It was a connection that we had specifically wired by hand, right? But then the wiring slipped. So the connection is either going to be a real link that we as engineers can follow, or it's a guess that our agents are going to make for us. And more, that agent is going to make these decisions, and it's making decisions that are important about people's very lives, right? Agents are now making decisions about hiring, right? So many of us are dealing with that right now. Agents are making decisions about legal issues. They're making decisions about money, right? What happens when your bank runs payroll off of an agent's judgment? You don't like Vibe payroll? That's not your favorite, right? So you're already seeing these alarm bells, but that's actually the direction that we're moving these days. And what happens when that specific guess that that agent is making is wrong, right? It doesn't break in your loop instantly, just like we showed in the code. It's not an instant outage, and there's no actual stack trace that we can follow. The agent answers confidently. It just blatantly lies, right? And then you found out weeks later in that war room, right, when there's no connections, no links, and no causal chain that actually allows us to trace down what's happening. So So let's picture a compliance tool that's at a bank, right? It's going to pull 3 different facts about a customer, Jessica. So Jessica's going to work at Apex Global. Apex Global is on the sanctions watch list, okay? Yikes. And Jessica is asking for a $25,000 credit line increase. Now, what should the agent do? Should it approve or reject this response? Yo, tank that thing, right? It should reject it. However, this agent specifically approved. Oh my gosh, this looks blaring, right? You and I, we can see these connections that are implicit within the agent right now. However, the agent itself, when it's oftentimes relying solely on a vector database, those implicit connections are too implicit to really draw, right? So you get this approval that we see here today. And the problem is every single fact was there, right? Every single fact was there, but that the answer that the agent gave was still wrong. Not that but not because the data wasn't actually tied to Jessica or to her employer or her employer to the sanctions watch list, but the agent needed a connection that actually wasn't explicit, right? So it did the natural thing and just supplied one, right? And now when people say this concept of hallucination, they're usually trying to picture like just invented facts. But this is a little bit sneakier than that, right? The facts are all correct. The facts are all real. When you are trying to go through this as in the war room, you're like, no, that's all perfect. Let me move to the next issue. What gets invented is the relationship between this data. And it's still a hallucination, but it's a little bit more dangerous because everything checks out and nothing looks wrong. So why did the agent approve this problem? Right? So MIT's NANDA initiative dug into this last year, and what I like to say to everyone is that never just blatantly believe the speakers who are up here, actually read the white papers that you see attached. So if you want to take a screenshot of the QR code, you can read the white papers. It's about 20 pages, 20-ish pages. It's very worth your time. But across the organizations, they had 95% of organizations they studied, 95% were getting no measurable return on generative AI. And what they blame is structural, right? They call it a learning gap. But the model is perfectly fine, right? The system that wrapped around that has nowhere to keep that specific context. No memory of what happened last week, no grip on the facts, right? And so no way for that agent to actually show its worth, no understanding of the connections. This is a common theme here, right? So most of us are going to build out retrieval-augmented generation pipelines, but it's going to miss that connection piece. And let's get specific about what that can look like. So to overcome AI's black box problem, where we're having no idea what's happening within our agentic systems, we need the knowledge itself to be transparent. So we see a human view of an apple in the center, right? And then we also see a vectorized view of an apple on the right, which is a series of floats or numbers. And it's not really human readable or understandable unless you've actually memorized the vector representation of an apple. And also every single object that's on Earth. And then on the left, you'll actually see a human readable and human understandable knowledge graph view of an apple, right? We have an apple, it comes from a tree, and that apple has a specific body, or look, it's round, and this one is red, it's the fruit, it's not the company. So knowledge graphs, and I'm going to get into this concept in a bit, knowledge graphs make what can be understood by humans and what can be understood by machines actually understandable by both. So it creates a fusion of both. And when an agent has to look something up, there are a few ways that it can do it. It can either do the vector search method, which is going to find meaning and proximity as well, or closeness using different algorithms like area nearest neighbor, for example. And it turns that text into numbers and then hands you back whatever the closest meaning is, right? And if you've built RAG pipelines, most of us are already just using pure vector stores or vector searches within our retrieval path. But graph traversal, on the other hand, finds the connections. You see those actual physical lines between those things? The lines are actually visible within knowledge graphs. It's both human readable and machine readable as well. And so the gap between both approaches is highlighted the instant a question needs what we call more than one hop, okay? More than one hop. A question or a query, for example, like, is this customer, Jessica, right, tied through her employer over here to a sanctioned entity, right? And vector search, it has no specific connections. All of it is approximate. And it can be calculated. I won't lie about that. It can be calculated, but on its own, vector retrieval is going to get you a long way. But today I want to teach you the second method to add specifically, not replace, to your vector retrieval pipeline that gets you the entire correct answer. And I want to make sure we're all starting on the same page, knowledge graphs. So I heard lots of people said that they've used graphs before. Have anyone used knowledge graphs before? Okay, a lot less hands, but a couple of folks. Y'all should be giving this talk. Why am I giving it? So all in all, can anyone tell me what a knowledge graph is? Silence. That's okay, that's okay. If you can tell me, I do have special swag for you. You can give your best stab at it.
It's a visual representation of the understanding of the links between the concepts of LLMs.
Beautiful. You get free swag at the end of this. Find me. Congratulations. Yes, yes, yes. So a knowledge graph is an organized representation, visual as well, of real-world entities and their relationships. So it's typically stored in a graph database, which natively stores relationships between data entities. So those entities specifically, we can see here, and I can give an example as well. I am a node here. Each node has a label. Think like table name for those who are a relational database folk, right? It can be person, transaction, foreign keys become relationships, etc. But I'm a node, and my new friend is also a node. And now we have a relationship that we are friends, right? So that's the structure. That's the entire structure of a labeled property graph and the labeled property graph model here. But properties on nodes and relationships work in a way that you can think of like columns, again, if you're a relational database person. And it matters specifically because you can store vector embeddings as well as properties on any node and then index them using approximate nearest neighbor search, like I had mentioned for vector space. And you get the graph traversal and vector similarity in the same database and all in the same query. There's no separate vector store, no data sync, and no eventual consistency between both systems. So that's pretty much what the model looks like. I mentioned before, y'all have said that you've worked with knowledge graphs. We see this connected data. And if we wanted to see what that looks like within a SQL, so if you were running an actual query, right? If you've written SQL or you've just written Prisma or Drizzle, for example, like you've described relationships before. You've done that work before. You've just never seen them very explicit. So on the left, right, this is a compliance check that has 4 different joins as well. That's going to join across 5 different tables. Now, don't clock out with me. I know this is a JS conference. I'm talking about data and databases. Don't clock out. Stay with me. But on the right, we have the same query, but written in Cypher. Cypher is a query language that is modernized and specific to traversing different graphs. But Cypher, we can see that the relationships are directly in the pattern. It's a little hard to see here because I couldn't get the Cypher syntax to work on Google Slides. But we have that we're going to match a specific customer ID. It's actually encompassed in these curled brackets. So that's the node. The curled bracket is the node. The customer who is employed by, and we have this directional arrow, by another node, organization. Pretty much the same as what we had here. Node employed by another node, okay? So we have that there. And then we can go through the Cypher itself, but it's flagged on this watch list, which has status active, and requested specifically this credit request has the status pending. What is the credit amount? And then return all the information about that person. It was Jessica. But what we see here is that text similarity often finds documents with similar meanings, right? But structural similarity, on the other hand, with graphs, finds entities with similar connections, and almost nobody is building out that second half, right? So every retrieval pipeline in this room, RAG, normal RAG, like hybrid search or re-ranking, it all operates on this single dimension, text similarity. Like how close is this specific chunk to this meaning in this query? And that work gets you about 70 or 80% of the way. But the second dimension, the one that a lot of people aren't building these days, is that structural similarity piece. Do these documents actually mean the same thing, right? Are these entities actually physically connected in some way? So how does this look like for connections that are trying to store the data? If you're coming from Postgres or MySQL or Mongo or whatever relational or NoSQL database, then you're modeling your connections with foreign keys to resolve them at query time, resolve them with joins at query time. However, there's this newer concept that I want to teach people about, which is not only building with knowledge graphs, but is building with this concept called context graphs. Now, context graphs has just pretty much made the waves within X and all these Hacker News, all these websites about December 2025. But has anyone heard of context graphs before? Yes, okay, like 1, 2, 3, maybe 3. Okay, so 3 folk. But in the present conversations around building AI agents, it shifted from using techniques for context engineering, using naive RAG, for example, to using graph RAG and knowledge graph augmented context, to now using what we call context graphs. And this is the summation of the entire talk, I would say. And it's not simply just a change in this terminology that we're seeing, but it's actually a conceptual difference, right? Context graphs, like I had mentioned, they made waves on Twitter, but it's all about highlighting and documenting this decision trace that we see. And I'm going to give a demo of this as well. But you're trying to make sure that your AI agent is like understandable, is trustworthy, is explainable, and you can actually trace what happened with your AI agent before. And you're going to use that with a knowledge graph and then this larger concept of a context graph as well. So usually, right, we have this big issue and why people have not used either context graphs or their agents have failed in the past. And specifically, some of those issues are that we have no memory, right? When an agent, if you ask an agent about last week's conversation, it has no idea what you're talking about, specifically especially when you're going to a new conversation if it's a conversational agent. But then you have no audit trail. When something goes wrong, no one knows why that agent decided that problem, and then there's no shared learning as well. We deploy multiple agents and they can't share what they've learned. So context graphs are fundamentally a knowledge graph that contains all of the information needed to make decisions throughout an organization. And this differs from simply opening up your agent to an audit trail, for example, which would have a line-by-line transaction history. But your agent now, with a context graph, it's going to have that breadth of knowledge, right? That breadth of knowledge from email threads to Zoom meetings, and it's all in a connected graph, right? Full of that context, and we have all of that information and all of that why. So here's a demo that I'm going to get into. I have it here hosted for you. If you want to follow along with the demo, you can see the link there. But let's get into it. If I can actually do this. Nope. Down. Yes. Sweet. Okay. So within this demo, and I'll skip all the backing information. But what's happening here? Right here we have this agent, and we're actually going to ask it to give us the entire decision trace history. So we're going to model the same exact concept that we had before. Should we approve a credit line increase for Jessica Norris? She's requesting $25,000 credit line increase. And if internet or the demo gods actually are in my favor, this is actually going to populate a graph and then populate the knowledge graph on the side of it. But what's happening in general is we're actually using natural language to search for customers and reviewing decisions and analyzing different patterns, right? You're asking your agent to access this entire context graph. Well, some things are happening, but that's okay. But then your agent is actually going to traverse the nodes and edges, and I'll make sure that I'm locked in, to traverse the nodes and edges to then expand and explore connected data. We might have to reload and re-ask. Let's make sure. Now I'm connected to Wi-Fi, so hopefully it'll work. But then it's going to trace the specific decisions, and on the right we'll see a full causal chain. And I really want this to work so that we can actually see this get populated live. But then lastly, the graph is going to use algorithms like FastRP, for example, KNN, and node similarity, Luvian, and PageRank, for example, all these different algorithms that provide structural or topological similarity that's normally impossible to do if you don't have a PhD in graph theory. So we're going to wait just a little bit. I'm a little tight on time, but if this doesn't work, then I do have a version, just in case. But the live is so much more fun. It's, no, that's okay.
That's in there.
Uh-huh. That's okay.
Yeah, that's plugged in, so I can't guarantee what's beyond that.
That's okay.
Though.
That's okay.
So, yeah.
That's all right. No problem. Well, the demo gods don't like me, but let's see if we can get it going. Anyway, okay. So at the end, and I know I'm tight on time, but I think at the end I can show you all. I'm just going to skip forward just a little bit just to show you all what the actual demo looks like. Okay. So what's happening here is what would have happened had Wi-Fi actually worked. So what happens here is that we actually see a recommendation from the AI agent, which is telling us to escalate for manual review. And eventually, we'll also see once we do this physical escalation piece, and then we save that data to the knowledge graph, it's then going to further populate that knowledge graph in real time, and then tell us to finally reject this request from Jessica on a number of different grounds, specifically based on the decision traces that we see on the right with a percentage accuracy, right? And so we see that we have a number of different requests, number one being that this request had failed based on a geographic anomaly, a timing anomaly. This request happened about 20-something times within a short amount of time, right? All this information is built into the context, which then we can see the entire decision trace. But you can read about this, and also, hopefully on your phone, it actually did generate. But all in all, let me skip back over. All in all, if you want to learn a little bit more about this entire concept, right, then I would very much implore you, number one, to understand these couple things, right? Number one, we want to build a system that cuts down hallucinations. Most everyone is trying to do that today. But number two, we want to force our agents to actually physically show their work. And they can show their work if they have a physical causal chain that they can traverse in order to get that answer and not have to assume based on an areas nearest neighbor algorithm or approximate nearest neighbor assumptions based within just using vector search. And so where you can learn more. So number one, you can learn more absolutely for free, all open source through Graph Academy. This is the absolute best place to learn more about graph algorithms, graph technology, as well as using graph plus artificial intelligence in order to build agents that are auditable and that are trustworthy, which is so important, especially, again, because these agents are moving from just asking and answering simple questions to actually making hefty decisions about our lives every single day. And then you can move from having this point where you're saying, oh, I have no idea how that agent actually made that decision, to actually seeing the full decision trace that your agent is able to provide to you when it comes to production going down, or when that lawsuit comes in and your boss is asking you, why did your agent make that decision? So thank you so much, everyone, for coming today. Please feel free to add me. Thank you. Oh my God! Thank you. Thank you.
Can you write my intro? I would love you to do my intro.
Oh.